Alright, so what I'm going to do in this video is just go through a few additional examples of symmetry adapted linear combinations. There shouldn't be anything really new here conceptually from what we covered in class, but these are a few examples that normally I would go through during class, but because of the hurricane we had to cut out some things. So I want to make sure that you have access to these. It's a good chance for you to get some additional work on symmetry adapted linear combinations if you think that's helpful. So the first thing I'm going to start with is one that I normally would have done right at the beginning, which is the symmetry adapted linear combinations for the sigma orbitals of ethylene. So basically we just have ethylene here. We're going to put a sigma bond just for the outer sigma bonds, the ones involving hydrogen. So I've labeled them as sigma 1, 2, 3, and 4 here. And we just want to figure out the symmetry adapted linear combinations. And one thing we're going to do as we go through this is sort of see the matrix origin of all of this too. Something else I didn't have time to go through in class, but is sometimes helpful. So the first thing we need to do is determine the point group of ethylene. So we should recognize that there's a C2 axis. It's a planar molecule, so there's one perpendicular to the plane. And then we can also find two additional C2s that are perpendicular. And because it's a planar molecule, it has a sigma H. So all of these together give this the D2H point group. Alright, so just like anything in this course, if you can't determine the point group, then you're pretty hopeless for getting the rest of the questions answered correctly. But we have the point group as D2H. And now what we're going to do is sort of show the matrix origin of all these. So as we said, there's a shortcut where, if we wanted to determine the characters for the representation that spans all of the SALCs, we just need to consider which of these orbitals move under the operation and which ones don't. So you should be familiar with the shortcut now, but I do want to give you a quick insight into the matrix origin of all of this. So if we apply the identity operation to this collection of sigma orbitals, sigma 1, 2, 3, and 4, we know that this is the do-nothing operation, so the result of that will be the same set of orbitals in the same order. We wrote this in matrix form. Alright, so that means if we want to represent the E operation as a matrix, we kind of did this before for x, y, and z coordinates, now we're doing it for a collection of orbitals. The E operation is just going to be a matrix with ones along the diagonals and zeros everywhere else. Write the numbers before the brackets, so the brackets should cover the whole thing. Alright, so this is our E matrix, and I already messed it up in the last row because I was, there we go. Alright, so all ones should be along the diagonal, of course. So this is the identity matrix, and then if we want to determine the character for this, it's just the sum along that diagonal. So the character under the E operation is going to be 4. So as we talked about, it's the number of orbitals that are unmoved under that transformation, specifically when we're talking about sigma orbitals, which can't change their signs under any of these operations. So the character would be 4. We could use a shortcut method to determine that faster, but that's the matrix form of it. Now if we do this one more time for another operation, let's do C2Z, which is going to be the one that's perpendicular here. So if we want to do the matrix form of this representation, or this character, we would do C2Z. So when we apply it to sigma 1, sigma 2, sigma 3, sigma 4 column matrix, so what's the result of this? C2Z is going to interchange sigma 1 and sigma 3. We're going to rotate like this. And it's going to also interchange 2 and 4. So what we would get is a new matrix that has sigma 3 in the position where sigma 1 used to be, sigma 4 where sigma 2 used to be, sigma 1, and then sigma 2 like that. So that's going to be the form of the matrix. That's going to be the matrix form of the result of that. And so if we want to write our matrix representation for C2 operation, the Z1 in this case, so what do we end up with? We would have a 1 in the third column for sigma 3, and then we have a 1 in the fourth column, and we have a 1 there for sigma 1, and then a 1 for sigma 2. So this is the matrix form of that. Everything is off diagonal here. All the non-zero elements are off diagonal. And if we sum along the diagonal, then of course we get a character of 0. And this is exactly what we would have found if we did the shortcut method. All of the orbitals move under this symmetry operation, so the character would be 0. Each would contribute 0. So that kind of gives you an idea of the matrix origin of all this. But like I said, we sort of went straight ahead to using the shortcut method. And so if we finish off the rest of these operations, so we said that the identity operation keeps all 4 of them in the same place, so the character is 4. C2Z moves all of them, and as do the rest of the C2s. So these perpendicular C2s are also going to interchange all the orbitals with each other. None of them will stay in the same place. You're going to have characters of 0 for there. Inversion does the same thing. The inversion center is right at the middle of the molecule, so you're going to invert 1 onto 3 and 2 onto 4 also, so that's a 0. The only other operation that has non-zero characters is sigma xy. So sigma xy is the plane of the molecule itself. So once again, all 4 operations, they don't move under that, all 4 orbitals don't move under that operation. So you get 4, but then for sigma xz and yz, we're going to reflect in these directions, and that's again going to interchange them with each other about those mirror planes. So those are the set of characters that we get for this, and so when we reduce this, we get AG plus B1G plus B2U plus B3U. Alright, so we get 4 sigma SALCs, all singly degenerate. So that's why initially I would have started with this one, because it's a little bit of an easier case than BH3, the first one we did with class, because you don't have any degenerate SALCs. You just have 4 non-degenerate SALCs. And so if we apply the projection operator to this, what we're going to again do is we're going to pick one of our orbitals as sort of their starting point, sigma 1 in this case. And then we're going to apply each operation and see the result of that operation. So the identity operation does nothing, so it returns sigma 1. If we do say C2Z, as we already said, sigma 1 interchanges with sigma 3 under that operation. C2Y, for defining the coordinates as y being vertical, it's going to interchange sigma 1 with sigma 4. So we put a sigma 4 there, and then C2X is going to interchange 1 with 2. So that's what we get for the first 4 operations. Inversion moves sigma 1 over to the sigma 3 position. Sigma xy, that's the plane of the molecule that keeps all of them in the same place, including sigma 1. So that is that outcome. Sigma xz is going to be this plane here. It's going to interchange 1 with 2. And then the last operation, sigma yz, is going to interchange 1 with 4. Okay, so that's the outcome of each operation on sigma 1. Remember, for the projection operators, we have to do each individual operation. Here, there's only one operation in each class, so our life becomes a bit easier. But in any point group, you'd have to apply each of the individual operations, not just one member from each class. And then we just multiply these by the characters. So from the character table, AG is a totally symmetric representation, so you're going to have 1s in each of those positions multiplied by the result of the operations. And then from the character table, we have these 3. We have the B1G, so we have to find the characters for that. B1G is 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1. So B1G is going to have 1 sigma 1, 1 sigma 3, and then we're going to have a minus sigma 4, minus sigma 2. We're just multiplying these by the characters, and then we're going to have a 1 sigma 3, 1 sigma 1, minus 1 sigma 2, minus 1 sigma 4. B2U, we have 1 minus 1, 1 minus 1, and then minus 1, 1, minus 1, 1. So this is B2U. We're also going to use this set of characters. And then the last one is B3U, which is going to be 1 minus 1 minus 1 1 and then minus 1 1 1 minus 1. Alright, so those are the characters multiplied by each of those results. And so if we write out the projection operators, then the AG projection operator gives us 2 sigma 1, 2 sigma 2, 2 sigma 3, 2 sigma 4. So all of them appear twice. And as we said, when you have a common factor, you can go ahead and factor it out right away. And so we get the totally symmetric additive combination, sigma 1, sigma 2, sigma 3, sigma 4. As I said, in most cases when you're dealing with sigma orbitals, you're going to have a totally symmetric form that looks like this. It's just an additive combination. Projection operator for B1G, we still have 2 sigma 1. This time for sigma 2 we also have minus 1 and minus 1, so we have a minus 2 sigma 2. Sigma 3 plus 1 plus 1, so we have a plus 2 sigma 3, and then a minus 2 sigma 4. So we factor out the 2's and we get sigma 1 minus sigma 2 plus sigma 3 minus sigma 4. So we have alternating in-phase, out-of-phase combinations. For B2U, as we'll see, we're going to have still 2 that are positive, 2 are negative. So we get 2 sigma 1s, we're going to get minus 2 sigma 2 again. This time we're going to get minus 2 sigma 3s as well. And then sigma 4 is going to be positive, plus sigma 4, plus sigma 4, plus 2 sigma 4s. Factor out the 2, we get sigma 1 minus sigma 2 minus sigma 3 plus sigma 4. And then we're starting to see a pattern emerge here. For this last one, we're going to also presumably have 2 positive 1 coefficients and 2 negative 1. And so what we get is, again, 2 sigma 1. This time we get plus 2 sigma 2. Then we're going to get minus 2 sigma 3 and a minus 2 sigma 4. Alright, so those are the collection of equations we get. We normalize them now. They're all going to have the same normalization coefficient. So as a reminder, the normalization coefficient is just the sum over all of the contributors to that SALC and the sum of the coefficients squared, and you take the inverse square root of that. So for each of these, it's going to be 1 over the square root. The first coefficient is always 1. The second coefficient is either plus or minus 1. And all the rest are plus or minus 1. So what we end up with for each of these is a 1 over radical 4, which is equal to 1/2. So the coefficient, if we're going to normalize properly, is going to be 1/2 for each of them. Again, that's just a mathematical requirement. It's not going to change the symmetry of anything that we're doing. And so if we write these out, then finally, we usually, again, use lowercase psi to abbreviate SALCs, and then lowercase Mulliken symbols as well. We get, for the totally symmetric A1, we get 1/2 times sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. For B1G, we get 1/2, and we get sigma 1 minus sigma 2 plus sigma 3 minus sigma 4. B2U, get, so all we're doing is just copying what we did in the last slide and then putting the normalization coefficient in front of it, so nothing difficult here. And then finally B3U. Okay, so if we want to draw out depictions of these, remember we use different colors, different phases to indicate whether it's added or subtracted in the SALC, whether it's in phase or out of phase. So the AG is totally symmetric, so it's going to look just like this, all of them in the same phase. And then for B1G, we get sigma 1 is positive, sigma 2 is negative, sigma 3 is positive, sigma 4 is negative. So the ones, this is a G SALC, so the ones that are related by inversion have to have the same sign. And then for B2U and B3U, we're going to end up with, for B2U, negative phases for sigma 2 and sigma 3, so we'll color those ones in. And for B3U, the last one, we're going to have negative phases for 3 and 4, so we'll color those two in. Alright, so that's what we end up getting for the 4 SALCs. One thing we can do also, we haven't talked about this yet, but it's something you should be able to do, is verify that the SALCs have the same, that they have the correct mulligan symbol. So in other words, we should be able to work backwards. So if I had given you this picture here, you should be able to figure out what the characters are and then match that to the character table. So if we do this for the B2U SALC that we just derived, so we derived the B2U SALC here. Now let's say I had given you this SALC and asked you what is the mulligan symbol for this. How do we go about doing this? So we apply each operation, and just like we saw before, if the orbital is unmoved under that operation, if it's unchanged, the character would be 1. If the orbital is inverted, if the signs are inverted, the character would be -1. And so if we go ahead and do this, what we'll end up with is, for the E operation, it doesn't change, of course. For C2 along Z, so that's the perpendicular C2, that's going to rotate everything, and it's going to change the sign. So this black or colored phase is going to rotate up to here and up to here, so you're going to get those up there. That's the negative of what we started with, so we can start marking these into the character table. So for the E operation, the character will be +1 because the orbital is unchanged. For C2Z rotation, we're going to change the sign of the orbital. Everything that was colored becomes white, everything that was white becomes colored. That means we're changing the sign of the orbital, or the SALC in this case. And so we get a -1 character there. For C2Y, we're designating Y as the vertical axis here. We're going to interchange orbitals that have the same phase, so we're not going to end up changing the overall sign of our SALC. So this would also be a +1 character. For C2X is horizontal C2. So when we rotate this, again, white's going to go on to color go on to white, and we end up with, again, the inverted SALC. So we're going to get a -1 character for C2X. This is a B2U SALC, so we should see a phase change under inversion. That's, again, what we do see, because we invert the two unrelated phases onto each other, so we end up with, again, the reverse. So inversion is going to have a -1 character. Sigma XY doesn't change the sign of any of our SALC because it's a planar molecule, so the plane of the molecule doesn't change the sign. These are all sigma SALCs, and so we get a +1 character for there. And then for XZ, that's going to be the mirror plane that sort of goes in this direction, perpendicular to the page. That's going to reflect it into the opposite orientation, and so we get a -1 character for XZ. And then for YZ, we should see that the sign is retained. We get the same phases where the two positive ones reflect onto each other, the two negative ones also reflect onto each other, and so that doesn't change the sign of the SALC. So we get a +1 character for Z. So we get 1, -1, -1, -1, 1, -1, 1. If we go back to the character table, if we hadn't already known this was B2U, we would see that that set of characters, 1, -1, 1, -1, -1, 1, -1, 1, matches to the B2U representation. And so we could figure out then that this is the B2U SALC, and verify that we did that correctly. And then also, if I had given you the B2U SALC without telling you its mulligan symbol, you could determine the characters and match it up using the character table. So that's one little wrinkle we haven't seen in class. Now the next thing I want to talk about for the SALCs of 1,3-cyclobutadiene, we did the pi symmetry adaptive linear combinations in class, so we'll have to refer back to those notes occasionally. If you're trying to follow along with this. But we did it assuming that we had a delocalized pi system, which sort of presumed also that it also presumed that all the bond lengths were equal and that the pi bonds were delocalized, as we said. Now let's see what happens if we localize the pi bonds, because one thing we found was that when we were doing the molecular orbital diagram, or at least the pi molecular orbital diagram for this molecule here, this delocalized form, we saw that the ground state was a diradical. We had 2 unpaired electrons. From that, we predicted it was unstable, and that's experimentally what's observed. Now, what happens if we do the localized form, where the 2 bonds are localized? So, this one, as we said, is D4H. The new point group we have to determine, because we're going to do descent and symmetry. So, essentially, what we're going to do is we're going to elongate 2 of the bonds. We're going to use descent and symmetry to figure out how the SALCs change in the new point group without having to go back and rederive all of them. So in the new point group we have a perpendicular C2, set of perpendicular C2 axes and a sigma H. So this is again D2H. We just did this point group for ethylene. But we have to figure out, if we're going to do descent and symmetry, we have to figure out which which of the operations are preserved, and so we can do the correlation correctly. So in this point group here, we have the perpendicular C2, of course, is preserved, and the C2 axes are the ones in this molecule that go like this and like that. In the D4H point group, we would have called these conventionally the C2 double prime. So it's those C2s that are preserved. Because we have two different classes of C2 operations in the D4H point group. We had to figure out which of those are preserved, and it's going to be the C2 double prime that's preserved, because that is going to change the correlations a little bit. So the other C2 axes which go through the carbon atoms, we called those C2 prime, and those are no longer present in the new point group. This doesn't have any diagonal C2s. It's a rectangular shaped molecule now. Okay, so the C2 double prime is preserved, and so we can go then and find the correlation. So in D4H, what we found was that the Mulliken symbols for the symmetry adapted linear combinations for the pi orbitals were A2U, B2U, and EG. Again, you can refer to that back in class. What date was that? I don't remember. That was last Thursday, I suppose, or last Tuesday, about a week ago. So check back in your notes to see how we got these symmetry adapted linear combinations. Now we want to correlate them to D2H. So if we go to the correlation table, here's the D4H correlation table. You might see something like this in certain versions of textbooks that you have. These are all the representations, or they're reducible representations for D4H. So this is what they correlate to in D2H. So we had a A2U SALC, and so if we go to D2H, preserving the C2 prime, again it's important to know which operations we're preserving, how the coordinate system is changing. So the A2U becomes B1U in the new point group. We have a B2U SALC, that's going to correlate with AU if we're preserving the C2 double primes. And then finally our EG SALC, we should recognize that D2H doesn't have any degeneracy, so our EG SALC is going to split, and in this case it's going to be a B2G and a B3G. Okay. If we had preserved the other axis, we would have gotten some slightly differences there. Okay, so those are the correlations. Then we know the Mulliken symbols. Now we have to figure out how do they change in the new point group. Now the first thing we have to do is we have to redetermine the degenerate SALCs. So as we saw in the, go back up to here, the EG degenerate set of SALCs in D4H splits into two, B2G and B3G. Because the degeneracy is lifted, we should redetermine those ones in the new point group. So if we go to the D2H point group, we can descend down to D2 to be able to just use a smaller set of operations. And so if we apply the operations to this set of orbitals, so if we're using phi 1 as our reference point, we get C2Z is going to take phi 1 onto phi 3. And the perpendicular C2s, if we have the Y, it's going to change it to phi 2. X is going to change phi 1 to phi 4. Alright, so we're going to redetermine the B2G and B3G SALCs using a smaller point group that still preserves the mixing of all the orbitals. In the D2 point group, did I give you that character table? I don't think I did, but the D2 point group, for those four operations, the characters for B2 are 1, minus 1, 1, minus 1, and then for B3 it's going to be 1, minus 1, minus 1, 1. So when we do this, we get a B2G SALC. It's going to be, if we normalize, 1/2 and then 1 plus 2. Alright, I messed something up here. Let me go back a little bit. So you have to remember the possibility of the signs changing. So when we do these operations on the pi SALCs, I was getting ahead of myself, getting too much of a hurry here. So C2Z is going to keep the sign the same. It's going to rotate perpendicular to the plane, so phi 1 is going to rotate onto phi 3. But when we do the perpendicular C2s, the ones that are in the plane of the molecule, C2Y is going to rotate phi 1 onto the negative of phi 2. Alright, because it's going to take this orbital here and it's going to flip it over and invert the sign. And similarly, when we do the C2 in the X direction, phi 1 is going to rotate onto the negative of phi 4. This black lobe, for example, is going to end up pointing down when we do that operation. So we should have negative signs there, and then when we multiply by the characters, what we'll get for B2G, we're going to get phi 1, and then we have a negative phi 2 times a character of 1. So we get minus phi 2. And then for phi 3, we have a positive character, but also a positive outcome with a negative 1 character. So we get minus phi 3. And then we're going to get a minus 1 times minus 1 plus phi 4. Alright, so it's important to remember, as I just forgot, that when you do operations on pi orbitals, you have the possibility of changing their sign. So then when we do B3G, we get a plus phi 2. And then we're going to get a minus phi 3 again, and a minus phi 4. Alright, so those are the B2G and B3G SALCs that we have in D2H. Remember that in the D4H point group that we started with, these were degenerate, and they had a slightly simpler form with only 2 of the orbitals contributing to each orthogonal SALC. So then finally we can construct a correlation diagram between the 2 point groups. So we saw that in the D2H point group we had an A2U SALC, we had an EG, so a set of degenerates, and then we had a B2U. Now we know from group theory what the correlations are in terms of the Mulliken symbols and the degeneracies, but if we go into, so this is D4H, we also saw that there's 4 pi electrons, so we had this sort of arrangement, as I said, the diradical. And then if we go and do the B2U SALCs, let's draw these out. So A2U correlates with B1U. So the B2U, so the B1U SALC in the localized model, the rectangular shape with, see, that's going to still be the totally symmetric one here. So giving templates for these. So we have this totally symmetric SALC. However, what we notice is that we're elongating 2 of the bonds. So we're elongating this axis and this axis. So we're decreasing the overlap between phi 1 and phi 4, phi 2 and phi 3. So we would expect this orbital to go up in energy a little bit. Because again, we're weakening some of the pi bonds. In the delocalized system, all the bonds are equal. Here we have 2 of them becoming longer, as we said at the beginning. So the B1U SALC is going to correlate to A2U, but it's going to be a little bit higher in energy. For the EG SALCs, they split, as we said, into a B3G and a B2G. Now the question becoming which one is lower and which one is higher in energy. And for that we have to use a little intuition. So the B2G SALC that we just determined is going to be 1 minus 2 minus 3 plus 4. So we get 1, and then we get this sort of relative phases. Okay, so that's sort of drawing the picture. And then for B3G, it's also going to be 2 in phase and 2 out of phase, and we're going to have this sort of B3G. Now, if we look at these symmetry adaptive linear combinations, you might think that these are pretty equivalent because we have, as I said, 2 in phase overlaps, 2 out of phase, or in other words, 1 node down the middle. But if we think about this a little bit more carefully, what we notice is that in the B2G SALC, the in phase overlaps are along the longer bonds. So, and then the out of phase overlaps along the shorter bonds. For B3G, we have in phase overlap along the shorter bonds, out of phase. So we expect to have stronger bonds in B3G because we have overlap on the short axis. The in-phase overlap is along the short axis. So we would expect the B3G to be a little bit lower energy and B2G to be higher. Alright, and that's again because of the in-phase overlap in B2G is along the long axis, so it's a weaker stabilization than we get for B3G, where the in-phase overlap is on the short axis. And then finally for B2U, we end up with an A2U SALC that it correlates to, and what does that look like? This is our A2U that I'm going to draw last. This is the one where they're all out of phase with each other, so you get alternating plus and minus coefficients, so everything's out of phase. Alright, so everything is out of phase in this cell. But what we notice is that we've elongated these two bonds here, and we're elongating along this axis to do this distortion, and so that weakens the antibonding interactions here and here, and along the left and right sides, so that we're going to have a slightly lower energy orbital because the antibonding interactions are weaker. So that's going to be our AU, predicted to be lower energy than the B2U. So we have to use a little bit of chemical intuition, a little bit of qualitative guessing like this to know which orbitals go up and down, but this should make sense based on our previous chemistry knowledge. And then finally we fill this with the 4 electrons, and what we notice is that when we distort the symmetry and we elongate along two of the axes and localize the pi bonds, we have all of our electrons are paired. This is predicted to be stable, or at least I should say more stable. Stable is a relative term. 1,3-cyclobutadiene is still not a stable molecule because of all the ring screening we have. But it's more stable than the delocalized form. So when you do observe even transiently 1,3-cyclobutadiene, it tends to distort and have more localized pi bonding to alleviate some of this, some of the problems with having this diradical and allow those 2 electrons to occupy a lower energy orbital. So this is predicted to be more electronically stable, and it is, and that's one thing we can use descent and symmetry to help us with understanding the correlations as we move from one point group to another. Alright, so a related system that I'll quickly do as a practice problem is the acyclic 1,3-butadiene in the anti-conformation. That means we have sort of this zigzag conformation as I'm showing here. So if we want to form a representation from the 4 pi orbitals and then determine the molecule symbols, that's all we're going to do here. We're not going to do projection operators. So let's just get practice again on determining the symmetry adaptive linear combinations and what their symmetries are. So we have a set of 4 pi orbitals, one on each carbon atom. Alright, for the first time today, we're going to move out of D2H symmetry. This is the C2H point group. So in this case, we have a C2 axis there, but we don't have anything perpendicular. So it's going to be C2H instead of D2H. That only has 4 operations. Alright, so when we apply these operations to the pi orbitals, under the identity operation, all 4 of them stay the same. The C2 operation, which is perpendicular, is going to rotate all of them. It's going to rotate the 2 interior ones into each other and the 2 exterior ones. So you get a character of 0 because all of them are moving. The inversion operation is going to also move all of them. It's going to change the phase, but it's going to move them to a new position. So these 2 are going to interchange with each other, as well as the exterior ones again, so we get a 0 there. Now sigma H is perpendicular to the plane of the molecule, perpendicular to the plane of the page, and that's going to invert the sign of every pi orbital. It's going to take the black and reflect it down to here, or the colored one, I guess, and reflect it down. So we get a -4 for sigma H, because each pi orbital stays in the same position, but changes its sign when we do a horizontal reflection. So then if we reduce this representation, we get 2Bg plus 2Au. We'll use this character table to do that, but I'm not going to go through all the details. So you can verify that yourself. One other practice problem, let's do the sigma SALCs for the chlorine atoms in this bimetallic here. So we essentially have 2 staggered square planar fragments, and we want to understand then the molecule symbols for the sigma SALCs that are formed from these. So this is going to be the D4D point group. Remember, when we have staggered arrangements like this, we want to think of D and D as sort of our first guess, and this is in fact D4D. So we want to determine the irreducible representations for the chlorine sigma orbitals. So we have 8 sigma orbitals, 1 in each position. For now, it doesn't matter how we number those. And so we're going to determine the representation for those sigmas. We have, these are the operations that we get from D4D. I think the character table is down here somewhere. So we have E, we have 2S8, We have C4, two more S8 operations, C2, 4 C2 primes, all classed together, and 4 sigma Ds all in the same class. So this is the D4D point group, and again, we're going to just apply each class of operations to our sigma orbitals and figure out how many of them move to a new position, how many of them stay the same, and so on. So if we have 8 orbitals, the character under the identity operation will be 8. Now we think about which of these operations move them to new positions. So here, if we do the S8, that's going to be an axis perpendicular here. That's going to rotate all of them to a new spot and reflect them over to the other side. So we'll get a 0 there. C4, which is collinear to that, we also get a character of 0 because they all move. S8 taken 3 times, character of 0, all of them move. C2 is along this same principal axis. So these first 4 operations after identity all share the same axis, and all of them result in movement. C2 prime, we have a bunch that are perpendicular, and that's going to interchange chlorine orbitals with ones on the other side. So that's going to move them all as well. And then finally, the only other operation that doesn't move all of our orbitals is sigma D. So if we think about how many orbitals are unchanged under sigma D, we will, for example, have the plane of the board as one of our sigmas. So it's going to be this plane here. It's going to keep 2 of the orbitals in the plane. It's going to reflect these 2, and it's going to reflect all 4 of these. And so we get a character of 2 for sigma D. 2 orbitals are in the plane for every reflection operation, and then the other 6 orbitals are out of the plane and they're reflected through that plane. Alright, so if we reduce this representation, we get our sigma orbitals come in as A1 plus B2 plus E1 plus E2 plus E3. So we get 3 degenerates and 2 non-degenerate. Now the next problem here asks us to apply the projection operator to derive the SALC for the least symmetric non-degenerate representation. So if you look at the degenerate representations we have A1 and B2. So we're talking about the least symmetric when we're talking about B2. So we're going to apply the B2 projection operator and find the symmetry adaptive linear combination for the B2. Now we have to think about how far can we descend in symmetry here, because as we said, for projection operators it's very helpful to descend to a lower order point group, but if we go all the way to C4 here, we're only going to interchange orbitals that are on one side of the molecule. So if we want to preserve potential mixing of orbitals that are on the opposite sides here, one on the first radium, one on the second, we need to descend into a dihedral point group. So we can only descend to D4 in this case, not all the way to C4. Okay, because the C4 point group does not distinguish A1 from B2, is another way to think about this. Alright, we also have to think about correlations here. So if we're talking about the B2 SALC in D4D, that's going to correlate to what in D4? So the B2 in D4D for the proper rotations is going to have characters of 1, 1, 1 around the principal axis, and then negative 1s for the perpendicular axis. So if we go down to the D4 character table, we want 1s for the first operations and negative 1s for the second. That's going to be A2. Alright, so this set of characters. So we have to be a little bit careful about correlations here, because the B2, again, the B2 representation in D4H, we're considering this character that's preserved in the D4 point group, this character that's preserved, that character, that character. So those operations are preserved in the lower order group. It's going to be 1s for the rotations about the principal axis, minus 1s for the rotations about the perpendicular axis, and that's what we got here for A2. 1s for the principal rotations, minus 1s for the perpendiculars. So we're going to be using the set of A2 characters in the D4 point group to do this SALC, so we have to be careful with correlations. And we have to apply each individual operation. So we're going to do the result of each operation on sigma 1. So we have E, C4, C4, 3. Alright, so if we apply the operation to sigma 1, identity keeps it the same. Let's make sure we number these up here. So we're going to call this 1, 2, 3, 4, 5, 6, 7. Alright, so if we do the C4 operation on sigma 1, if we do a clockwise rotation, I'll take it to C2. We rotate in this direction. So that's going to take sigma 1 on a sigma 2. It's going to take sigma 1 on a sigma 4 if we do the counterclockwise. And then the other rotation about the principal axis is going to take sigma 1 onto sigma 3. Alright, so the first set of operations on the principal axis interchange sigma 1, sigma 2, sigma 3, and sigma 4. Now for the perpendicular C2s, it's a little bit arbitrary what we classify as C2 prime and C2 double prime, but essentially we're going to have a set of operations that interchange sigma 1 with all of the ones over here. Alright, so if we draw sort of a down the axis representation of this, so we're looking down the rhenium axis in this case, perpendicular how I have it drawn. If you have your sigma 1, sigma 2, sigma 3, sigma 4, and then on the other side you're going to have 5, 8, 6, and 7, something like this. So these C2 prime operations are going to interchange sigma 1 with all of the rest of them. You're going to have one that goes sigma 1 to sigma 8, sigma 1 sigma 5, 1 and 6, 1 and 7. So in some order, you're going to get this outcome for the perpendicular C2s. You're going to interchange sigma 1 with all the ones on the other side for the 4 different C2 operations that are perpendicular. And then we multiply these by the character for the A2 representation in D4. As I said, that's the representation we're considering as correlating to the B2 in the other point group. We get plus 1s for the principal rotations, minus 1s for those, and so what we end up with is the projection operator applied to sigma 1 gives us 1 plus 2 plus 3 plus 4, and then we get minus 5, minus 6, minus 7, minus 8. So in other words, this is an out-of-phase combination of the 4 sigma SALCs on these with the 4 sigma SALCs on the other side. That's a little bit of a weird one. We'll talk more about metal-metal bonding later, which is, I think, the more interesting part of these types. But again, we can use the same approach that we developed for determining symmetry dappled linear combinations for metal ligand sigma orbitals as well. The last thing I want to talk about are SALCs for non-equivalent positions. So a non-equivalent situation is one where we already saw it for 1,3 cycle beta diene, although we didn't do projection operators, but it's a situation where the operations in the point group do not interchange all of the orbitals with each other. So if we look at C2V example SF4, this sort of seesaw-shaped molecule here, what we'll notice is that the operations will interchange sigma 1 and sigma 2, or sigma 3 and sigma 4, but there are no symmetry operations that interchange 1 with 3 or 1 with 4. Similarly, there's none that interchange 2 with 3 or 2 with 4. So not all of the orbitals are interchanged on the operations. Now there's a couple ways that we can do this. The first way is just to sort of start with, just ignore the fact that we have these non-equivalent positions and just do the reducible representation for all 4 basis orbitals and then apply every single projection operator. Alright, so if we do this for all 4 sigma orbitals in the C2b point group, we have 4 orbitals, so we're going to have a character of 4 there. The C2 operation is going to move all of the orbitals onto other positions, we get a 0 for that. And then for XZ and YZ, as I defined it here, the XZ is going to keep sigma 3 and sigma 4 in the plane, and then the YZ, which is the plane of the board in this case, is going to keep sigma 1 and sigma 2. So both of those are going to have characters of 2. For those 2 operations, it's a little bit arbitrary how I chose this to define the coordinate systems here, but conventionally you put more of the more atoms in the YZ plane than the XZ plane, but it doesn't really matter in this case because there's the same amount. So at any rate, however you chose to define those, though, you're going to have characters of 2 for XZ and YZ. So if we apply all the projection operators, if we apply the projection operator starting with sigma 1 and do all the operations, so C2 moves sigma 1 to sigma 2, sigma xz, which is perpendicular to the board, is going to interchange 1 with 2 also, and then yz, which is the plane of the page, is going to interchange 1 with itself. So that's the result of doing the operations on sigma 1, and as I said, because you have non-equivalent position, the operations only interchange sigma 1 with sigma 2. And then if we apply all of the projection operators, so when we reduce this set of characters that we got up here, we get 2a1 plus b1 plus b2, and so we're going to apply all of those to sigma 1. So the a1 projection operator is a set of characters that are just 1, 1, 1, 1, and so this is approximately equal to sigma 1 plus sigma 2, an in-phase combination. For b1, we get characters of 1, minus 1, 1, minus 1, and so when we add these together, we get sigma 1 minus sigma 2 plus sigma 2 minus sigma 1. So the sigma 1s cancel out, sigma 2s cancel out. This means this equals 0, and what this tells us is that there is no b1 SALC that involves sigma 1 and sigma 2. If we do it for b2, we get 1 minus 1 minus 1, 1 for the characters. Those come from the character table, which I think I have down here. So we're doing a1, b1, and b2. We get 1 minus 1 minus 1, 1, and then we'll see this is a subtractive combination, sigma 1 minus sigma 2. Gives me the negative 1s in front of sigma 2, positive 1s in front of sigma 1. So those are the two symmetry adaptive linear combinations for sigma 1 and sigma 2, just an in-phase and an out-of-phase. If we apply then the projection operator to sigma 3, so we didn't have any contribution from sigma 3 and sigma 4, so we have to do this again to incorporate those two orbitals. So the E operation keeps sigma 3 in the same place. C2 is going to interchange sigma 3 with sigma 4. Sigma xz is the plane of the board that includes sigma 3 and sigma 4, so that keeps them the same. And then the yz, which is the plane of the page itself, is going to interchange sigma 3 with sigma 4. And then we again apply all of the projection operators. We have an a1, a b1, and a b2. So for a1, we again get just an in-phase combination, sigma 3 plus sigma 4. For b1, the characters again are 1, minus 1, 1, minus 1. In this case, we get sigma 3 plus sigma 3 minus sigma 4 minus sigma 4. So this is the out-of-phase combination, sigma 3 minus sigma 4. I should say approximately equal to that. And then finally for b2, we get 1, minus 1, minus 1, 1 for the characters, and we see that they cancel out again. Sigma 1 minus sigma 3 minus sigma 4 plus sigma 4. So this one equals 0. So that means the b2 SALC, as we determined above, doesn't include sigma 3 and sigma 4. So this was sort of a slightly longer way of getting all four of the SALCs. We have just in-phase and out-of-phase combinations of 1 and 2 and 3 and 4. There is a slightly shorter way to do this, which is to recognize ahead of time that we have non-equivalent positions. And then the way we can deal with this instead is we derive representations that only include sigma 1 and sigma 2, and then we derive a second set of representations that only include 3 and 4. So when we do this, if we derive a representation for sigma 1 and sigma 2, those are the positions that are equivalent with each other or that are interchanged under the operations, we only have two orbitals there. C2 moves them both again. Sigma xz moves those two orbitals, but then sigma yz is the plane, so it's going to include sigma 1 and sigma 2. And so this is a1 plus b2. So the two symmetry adaptive linear combinations that include sigma 1 and sigma 2 are going to be a1 and b2. We do the same thing for 3 and 4. We get a 2, we get a 0. In this case, sigma 3 and sigma 4 are in the yxz plane as I defined it. Xz. So it's going to keep that as 2, and then yz is going to reflect them. And this comes out to a1 plus b1. So when we do it this way, we only apply the projection operators that apply to each set of orbitals. So sigma 1 has only a1 and b2 representations, and so when we apply the projection operators for sigma 1, we still have to apply all the operations. We get sigma 1, sigma 2, sigma 2, sigma 1. We saw that on the last one, so I'm not going to go through that again. And then we only have to multiply the characters for a1 and b2. So we get 1, 1, 1, 1. 1, minus 1, minus 1, 1. So really, these two methods are about the same amount of work. It's just whether you choose to recognize at the beginning that we have non-equivalent positions, or you just apply every single projection operator and find that out sort of the hard way. So it doesn't really matter how you do it. Both of the methods I'm showing you here are valid, and at least for a small point group like this, they're a similar amount of work. If you had a larger point group with more orbitals to consider, more operations, more SALCs, you may want to recognize at the beginning that there are non-equivalent positions so that you can save yourself some work when you're doing the projection operators. So for sigma 3, we're only going to use A1 and B1. Those are the only two representations that came out when we reduced the characters for that. And so when we apply the operations, just as before, we get sigma 3, sigma 4, sigma 3, sigma 4. The characters for A1 are all 1s, so that comes out to sigma 3 plus sigma 4 in phase. Characters for B1s are all alternating 1s and minus 1s, and so we get sigma 3 minus sigma 4. Alright, so those are two different ways of determining the symmetry adapted linear combinations. They both work equally well. And then from there, we can start mixing them with atomic orbitals. So for the A1 SALCs, we have, if we normalize, 1 over radical 2, and we have in-phase combinations of sigma 1 and sigma 2, and sigma 3 and sigma 4. So we have two A1 SALCs. They can't be degenerate in this case because we don't have degeneracy in this point group. They're non-degenerate representations. And the atomic orbitals that have the A1 Mulliken symbol, that have the same symmetry, would be, this is SF4, so we're in the third row of the periodic table, so it's going to be 3S, and then if we go to the character table, A1 also transforms as Z. So the PZ orbital is also going to be of A1 symmetry, and so we would have two possible mixings. If we look at pictures of these, the first A1 SALC is sigma 1 plus sigma 2, which are the ones on the outside here. That looks like it would overlap well with the 3s orbital, and then the other A1 SALC is the in-phase combination of sigma 3 and sigma 4, which are those ones, and we can imagine a pretty strong overlap with the PZ orbital. Now in reality, when we have this situation here where you have two atomic orbitals that are A1 as well as two SALCs that are A1, you're going to get a lot of mixing. So your molecular orbitals are not going to necessarily be pure, this one and this one. It's going to be a more complicated mixing scenario where you get some character from all of these. And that's, we can't use symmetry to predict that. That depends on the relative energies of the 3s and the 3p and how well they mix with each of these SALCs. But at any rate, we can sort of draw these as sort of the limiting depictions and the ones that we think are going to be the strongest contributors based on symmetry. This set of orbitals would have the best overlap with the 3s orbitals. This set of sigma orbitals would have the best overlap with the PZ. Now if we go to the B1 SALC, we saw that had the form of out-of-phase combination sigma 3 minus sigma 4. From the character table, B1 transforms the same as X, so it's going to be the PX orbital. And in our orientation, that's the one that is into and out of the board. There's two ways to draw this. So the x-axis, as we said, is into and out of the board. If we rotate this whole thing, what this would look like is it's an out-of-phase combination of those two SALCs, and then that's going to overlap with PX. So we're putting here the x-axis is horizontal. If we look at the normal view, as I gave it above, we had sort of this viewpoint of the seesaw. And so you'd have sort of this perpendicular overlap here. So it's a little bit harder to draw in this orientation. But anyway, it's a out-of-phase combination of sigma 3 and sigma 4, and we get good overlap with the 3px orbital. And then finally for the B2, we saw that was out of phase sigma 1 minus sigma 2. In the C2b character table, B2 transforms as Y, so that's going to match with the 3py orbital. And so if we draw this, and again the normal orientation here works just fine, this is out of phase combination of those two sigma SALCs, and that's a perfect symmetry match with the 3pz orbital. Alright, so that's what the orbitals look like. The orbital energies will be a little bit more difficult here because they're all sigma, and as I said, there's going to be a lot of mixing, especially with the 3s and the 3pz. So it's a little bit harder to draw a specific diagram for this. I'm not going to attempt to do that, but we can at least use symmetry to figure out what the orbitals themselves look like, and these are going to be all the sigma bonds between the central atom and the 4 outer atoms, in this case SF4. Alright, that takes us to the end of what I wanted to cover today. I just gave you a quick rundown of some additional SALC problems. I went through these a little bit fast on purpose, but you're welcome to, and I encourage you to spend more time on this yourself. And if you have any questions on it, of course, please come and see me. These are definitely good examples of some of the things we've learned in class. Alright, I'll see you guys in class soon.